Okay, we're going to continue on here talking about thermodynamics here in this chapter. So last time we continued our talk of thermodynamics, and we obviously finished up previous to that delta S, which is our entropy. We got into our delta G, which is our Gibbs free energy. And we saw so far a couple different ways that you could kind of calculate delta G. One is just like normal, you could take your delta G of your products from the table minus your delta G of your reactants, just like you do with pretty much all the other thermodynamic values. You look them up in the table, you multiply by the coefficient in the balanced equation, and do products minus reactants. As we talked about, that's basically kind of your final state minus your initial state in a chemical reaction. We also saw a delta G that actually involved some other thermodynamic values like this guy here. And that's our delta G is equal to our delta H minus T delta S. This obviously being our enthalpy, that being our entropy, and that obviously being our free energy there. And our temperature in Kelvin, right? This case. So remember, as we talked about last time, you do want to watch units on this particular equation for sure. Again, in terms of the units, delta H's are typically kilojoules, delta S's are typically joules, and delta G's are usually in kilojoules as well. So the units of this guy and this guy are oftentimes, about 1,000-fold difference, as S is usually in joules and the other guy's in kilojoules. So you typically do need to do some type of conversion to get them into the same unit. Otherwise, again, you'll find yourself off by a factor of probably like 1,000 or so. The nice thing about Gibbs free energy is we could use the delta G value, and if it is negative, it will tell you if it's a spontaneous reaction. If the delta G is positive value, it's non-spontaneous as it's written, and at equilibrium, delta G will equal 0. Again, in an equilibrium process, because the rate of the forward reaction and reverse reaction are basically occurring at the same time, there's kind of no net change. Everybody gets locked into place, so there's not a lot of change that's going on in terms of the reaction. Remember, for delta S, it is the delta S of the universe, right? That we need to calculate, which is our delta S of our system plus the delta S of our surroundings. So that is, again, what we have to use to try to determine if something is spontaneous. Any questions on that stuff we talked about last time? I think we finished up last time looking more at this equation. And again, depending on whether your delta H is positive or delta S is positive or negative, you can make a relatively good prediction as to whether or not the reaction will be spontaneous at, say, a low temperature, high temperature, any temperature type of situation. So let us continue on then. I think, yeah. Right. So remember, when we look at delta S, and it depends which delta S you're talking about. So if you're talking about the delta S of the system or the reaction, it will not tell you if the reaction is spontaneous or not, but what it will tell you is whether or not that reaction is increasing the disorder or decreasing the disorder. You do have to calculate the delta S of the universe to determine if the reaction is spontaneous. And if you calculate delta S of the universe, what you would have to do, obviously, both of those things, the system and the surroundings, to get there. If you calculate delta S of the universe and it's positive, then it is going to be a spontaneous reaction. And if it's negative, it would be a non-spontaneous. But you can't just solely look at like the delta S of the reaction or the system to do that. And the delta H really won't tell us anything about spontaneity other than the reaction is kind of exothermic or endothermic. And remember, exothermic does sort of help with spontaneity, but we saw some reactions and stuff that were sort of endothermic and still spontaneous. So it really won't tell you that. So you can definitely use delta G to determine spontaneity. You can use delta S, but you have to use the delta S of the universe to determine it as well. In order to make that determination if the reaction is spontaneous or not. Yeah. Other questions? Okay. So let's take a look at this here. Let's say we're doing this reaction here, a little decomposition reaction. So why don't you calculate the delta G at 25 degrees Celsius and determine, is this reaction spontaneous? Let's see what you come up with here. We have our delta H and our delta S given to us. So here we do want to use our delta G is equal to our delta H minus T delta S. We would need to add obviously 273 here to convert us into Kelvin. And then we're pretty much good to go to punch it into there. Maybe. So let's go with our delta G here is going to equal, I am personally going to multiply our delta H by 1,000 to convert it into joules. And I'm doing that because my S is in joules. You could obviously go the other way and convert the S into kilojoules, but you do need to do some type of conversion, whatever you like to do. Then we're going to go minus our T and our delta S, which is 160.5 joules. All right, so if we do that there, 177.8 times 1,000 to convert it into joules, minus 298 times my 160.5 joules. So everybody's in the same units. That's going to give me a 129,971 joules. You can divide it by 1,000, and that will give me roughly 130 kilojoules here of our delta G. Any questions first off on that calculation there? Is this reaction spontaneous under these conditions? The answer is it is not spontaneous, right? And that's because we got a positive delta G. As we talked about last time, we could have probably made that prediction based on the signs that we see for each of these. That was a positive value. This is a positive value, which means the only way for this negative guy to overtake the first number is it would have to be a really large temperature. And 25 degrees is not going to cut that, again, because delta H is in kilojoules, the other guy's in joules, so it's got like 1,000-fold jump on it to begin with. So that's why we see here is non-spontaneous. So can we figure out when the would become spontaneous, at what temperature that might occur? And we can. So we could actually use our same equation here. And we know that in order for this reaction to become spontaneous, delta G has got to be negative. So that is the other side of zero, basically. So 0 equals our delta H minus T delta S. If I rearrange this and solve for my temperature here would be the delta H divided by the delta S. And again, in this case, we do have to be careful of units. So once again, I'm here. Once again, I'm going to multiply my delta H by 1,000 to put them into joules. Again, you could go to kilojoules if you prefer. And I'm going to divide this by my delta S there, which is in joules. That way those cancel. And obviously the Kelvin's still there, so Kelvin will pop up on top when we do that. 177.8 times 1,000 divided by 160.5. Going to give us roughly 1,108 Kelvin, which if we subtract 273 from, would give us approximately 835 degrees Celsius. First off, any question on that calculation? Yeah. Yeah, so pretty much you could use this equation if you have the H and the S, and if you find that the reaction is non-spontaneous but want to know what temperature it might turn spontaneous, you could do this calculation with it. If the reaction was spontaneous, likely you probably might not be asked that question as to what temperature it would become spontaneous. You may be asked, like, what is the minimum temperature maybe that it would become spontaneous? And that's basically what this number represents, is the minimum number at which this reaction then becomes spontaneous. Yeah. So you might have a question like that. And we could also see that this value is a small temperature, large temperature. It's a pretty high temperature. Yes. And that is what we predicted, right? Again, based on the signs that we had for both of those guys. clearly 25 degrees is not going to cut it. We need 835 degrees Celsius, which I would say is a high number. We see that in the graph actually here, which is good. And what we actually see is we're looking at pressure versus temperature. And because this is the only gas in this particular reaction, the only way we can get pressure is to make that gas, right? And we pretty much see all the way up before then, we have no pressure, which means we didn't make any products. So we have no gas molecules flying around. We actually start a little bit before 835, starting to actually make those products, but it doesn't hit sort of standard pressure, which is 1 atmosphere, until about 835 degrees Celsius. So that's usually sort of considered the minimum temperature that you would need to get this reaction to do it. Or obviously any temperature higher than that should successfully get that reaction to become spontaneous. Any questions on that there? All right, so let's try one here. For the following reaction, delta H is minus 1204, delta S is minus 216. Are the reactants or products favored at equilibrium under standard conditions here? Delta H given to us, we do have the delta S given to us. So once again, we're going to use the appropriate equation here to do that. And we just need to do a little same conversion there, or convert that guy over into Kelvin by adding 273 to it. And then we're ready to sort of plug it in. Once again, just like I've done previously, I'm going to multiply by 1,000 here to turn this guy into joules, so I don't have any type of unit problem. And also, like normal, you can go the delta S into kilojoules if you prefer. So if we do that there, we are going to get minus 1204 times 1,000 minus 298 times minus 216.4 in this case. Going to give us negative 1139513 joules, or again, I'm going to convert it back now into kilojoules by dividing by 1,000. Negative 1140 basically kilojoules here. Any questions on that calculation there? Now, we do see a negative value here for delta G, which means this reaction should be sort of favored heading towards the product side in this case, right? And would be technically kind of spontaneous. And since it is, it should be heading in that forward direction, making products. Any questions on that calculation there? All right, so a main thing on this one, again, is just units. And it's a very common thing. People overlook the kilojoules and joules sort of difference. And then you find yourself again off by a factor of 1,000 probably. All right, so let's talk a little bit about Gibbs free energy and phase changes. We touched a little bit upon it earlier there when we were talking about the third law of thermodynamics. But when we do phase changes, as we talked about, that is an equilibrium process. So when you take a substance, say, from solid to liquid or liquid to solid, that does occur at the same temperature, which is the normal melting point, freezing point of a substance. When you take a solution or something from liquid to gas or gas back to liquid, that also occurs at the same point, and that's the normal boiling point of a substance when that occurs. We talked about, I think, the other day as well, that there is a certain amount of heat required to do those phase changes. The heat of fusion is the energy required to go from solid to liquid or liquid back to solid. It is the same number regardless of which way you go, but the sign is different, as one way is exothermic and one way is endothermic. And going from solid to liquid is a endothermic process. Going from liquid back to solid, you need to release the energy, which would be an exothermic process. And that would obviously just change the sign of delta H of fusion. We also have one that covers, again, the liquid to the gas transition going in both directions. And that, again, is a delta H of vaporization for a substance. And it works the same way as we go from liquid to gas. You just put energy in. As you go from gas to liquid, you have to release that energy. So the delta H of vaporization should be negative for those guys. At exactly those points, either the melting point, freezing point, or the boiling point, again, we do have both of the phases in equilibrium with each other. And because of that, That means if we look at our equation we've been looking at, our delta G will equal 0 because it's in an equilibrium process. Now, if we rearrange this equation and solve for the delta S, and if we do it for here, which is liquid to gas sort of transition, so that is our delta H of vaporization that's needed to do that. We could solve for the delta S, which is actually in this case what is sometimes referred to as the delta S of vaporization. That's the entropy change as you go through the process, basically, of vaporization or evaporation. And what we see here is a couple of things. This is water, so these values are obviously specific for water. That is the delta H of vaporization for water. It's about 40.8 kilojoules per mole. This is the normal boiling point for water, right? It's 100 degrees Celsius, which if you add 273 to it, gets you 373 Kelvin, right? So that is where that number comes from. And what we get here is a entropy of vaporization of 109 joules per Kelvin. What we see on the entropy of vaporization is it is a positive number, which means is order increasing or decreasing here? The amount of disorder is increasing, right? The amount of order is decreasing, however you want to look at that. Remember, delta S with a positive value, right, is a increase in disorder, right? And that's what we would assume as we go from liquid to gas, because we're obviously going from a more ordered state in liquid to gas state where they're flying around, right? Now, if we did this, say, in the opposite direction, like gas going to liquid water, right? This way, liquid water. The only thing that would change here is what? It would be the sign on the delta H of vaporization. This would be then negative 40.79 kilojoules over 373 Kelvin, gets you a negative 109 joules, right? And that also makes sense as we go this way. This is sometimes maybe referred to as a delta S of condensation, right? That's condensation going from gas where everybody's flying around to liquid where they're more stable. And obviously we would see a decrease in the disorder, and that represents the negative value there that we see for our delta S going in the opposite direction. First off, any questions on that there? This is also the equation where people screw up because they want to put an extra negative in there. If you get this equation derived from this formula here, it is the delta S is equal to the delta H over T, right? And that is the one that you would use for some type of phase change. I am pointing this out because earlier on when we talked about delta S, we saw this equation, which is delta S of the surroundings minus delta H over T, negative, yes? So if it is surroundings, you need that negative, as we talked about, for the opposite relationship that occurs when energy leaves. If you're just doing sort of a phase change and trying to figure out the entropy for a phase change, there is no negative in that one. So again, that's a common sort of mistake that sometimes people will make. Any questions on that? Yeah. When it goes from gas to liquid, the delta H would be negative because it's exothermic. So you have gas molecules flying around. In order for them to come out of the gas phase into the liquid phase, they basically got to slow down, right? So they slow down and has to lose energy. So they actually give off the energy. And as they give off the energy, they no longer have enough energy to escape each other as they're flying around. So they kind of clump and drop into the liquid phase. So that process of going from gas back to liquid is an exothermic process, which is why the delta H would be negative in this case. And it would be a positive value going from liquid to gas because it actually has to absorb the energy in order to kind of break away from each other in a liquid phase to start flying around in the gas phase. Yeah. Yep. Other question? And just in general, right, if you think about the phases as you go from solid to liquid to gas, those are all processes where energy has to be put in for those things to happen. And they're all endothermic processes. And they all would be really positive values for like any type of energy value going that direction. And it's opposite as you go the opposite way here from gas to liquid to solid. Those are all processes where those things need to release the energy to slow down and kind of clump together. And those would all be negative sort of values heading in those directions. Other questions? All right, so I want you to give this a try. The enthalpy of vaporization for mercury is 58.5. The normal boiling point is 630. What is the entropy of vaporization for mercury in this case? Okay, let's take a look. So the enthalpy of vaporization is our delta H of vaporization. And for mercury, it is this value. Also a reminder, sometimes we always focus on water. So obviously if we're not using water, the delta H of fusion, which is 6.02, and the delta H of vaporization, which is that 40.8 number, would be different for a different substance. Also, the normal boiling points and melting points would be different than obviously what it would be for water. So in this case, we're dealing with mercury, which as we see here has a much different boiling point than water at 100 degrees Celsius, which is 630. So this is really a phase transition here. So we're going to really derive our equation here from our delta G equation. And again, because we're at equilibrium, which is when this occurs, our delta G will equal 0, which gives us 0 equals delta H minus T delta S. Here we are looking for S, so we'll bring it to the other side. T delta S equals delta H, and dividing it out gives us over T, which in this case would be our vaporization. So putting our numbers in here, it is an endothermic process as we're going from liquid to gas in this case, which is vaporization. So I am, again, here going to multiply by 1,000 to convert it to joules. And our temperature actually is already in Kelvin, which is good. And that would get us 58.5 times 1,000 divided by a 630. Gonna get us a 92.9 joules per Kelvin. The reason I convert it to joules again is delta S is typically given in joules. Obviously, if you did kilojoules, you would be 0.92 there. Yeah. Okay. Okay, first off, this does make sense in the transition of going from liquid to gas, as we were talking about. We would expect this value here to be positive as we're increasing the amount of disorder. Once again, if we were doing something like condensation heading in the opposite direction, again, the only thing that would really change is we would insert a negative value here, and that obviously would then turn our delta S into a negative, which would also make sense, again, going in that reverse direction, going from gas back to liquid. Any question on phase changes? Yeah. I would think you need to at least show this. It might be helpful so you don't maybe insert an extra negative that shouldn't be there just for yourself, but you need to at least show the bottom part. Yeah. Yeah, it's okay. Yeah. Other questions? All right, so let's talk a little bit about our friend equilibrium and Gibbs free energy because we haven't seen K here in a bit, so sad. But let's first talk about one where we don't have K there. And this equation here, which is our third equation that involves delta G. And just to make things better there, we actually have two different delta G's sort of happening here. We have delta G is equal to delta G naught plus RT natural log of Q. So once again, as we talked about previously, when you see those little knots next to sort of the letters like delta G, delta H, delta S, again, that usually indicates sort of standard conditions. And I think we talked about it last time. When we kind of talk about standard conditions, that usually means that the pressures, if there is pressure involved, is 1 atmosphere. The molarity should be 1 molar if there's solutions. And usually the temperature should be 25 degrees Celsius. So those again are sort of standard conditions. Those are kind of like what you find in tables that you would go look up values in. So this delta G, one way you could kind of think of it is sort of the delta G under non-standard conditions. So something is not one of those things. So maybe the pressure is not 1 atmosphere for everybody. Maybe the molarity is not 1 molar, or maybe the temperature is not 25 degrees. So something is under non-sort of standard conditions. This delta G naught is basically delta G under standard conditions, where you could go look up the values and do something like your products minus your reactants, right? Which may be given to you in a problem, or you may have to actually go calculate that yourself. Again, in most cases, you would probably do products minus reactants to get that value. R is our gas constant, and it is the one that involves energy. It is the 8.314 version. T is our temperature, which should be in Kelvin. And Q is our reaction quotient. And if you remember our reaction quotient, we've seen it in a couple different places, but it is basically calculated the exact same way as you would calculate K. So remember, Q is basically calculated the same as K, which means Q would be the concentration of your products or your pressures, if you have pressures, divided by your reactants. Once again, we use the coefficients as the exponents and all those good things. So this will allow you to calculate delta G in a sort of non-standard condition. And who knows, maybe in a standard condition, the reaction would be non-spontaneous, but maybe playing with pressures or playing with concentrations, you may be able to turn that non-standard reaction into a spontaneous reaction afterwards, or you may not. When we do get to equilibrium, a couple of things happen. Our delta G equals 0, and we're no longer talking about Q. We should have the equilibrium constant. So basically rearranging the top equation here, putting this guy as 0, will allow you to get to this equation here, which is the delta G naught is equal to minus RT natural log of K. And those are the same sort of characters. That's our delta G under standard conditions. R's are 8.314, our temperatures in Kelvin, and K is our equilibrium constant. So products over reactants, just like normal. Couple of things about each of these. Again, our signs. So people always want to, on the top one, subtract the back part there. So it is plus RT natural log of Q. And on the bottom one, people always forget the negative. Yeah, so that is negative. And again, it's derived from the top equation. So where should you use these type of equations? Clearly, again, the same message applies. If you got something that involves the equilibrium constant, either it's given to you, you're trying to find it, then probably the bottom guy there is your equation to use. If you got something where maybe they give you concentrations, they give you pressure, something that's non-standard type conditions, then probably the top guy up there is going to be the one to use. And then obviously, as we saw previously, if you have a delta H or a delta S given to you, then the G equals H minus T delta S is a good one. And lastly, if you have really nothing given to you other than maybe just the equation, then products minus reactants, look them up in the delta G formation sort of table. Any questions on any of those there? All right, let's try some here. But we can obviously look at this equation. And really the nice thing about this equation is it does have the equilibrium constant. So I would hope at this point you understand the idea of the equilibrium constant. If you don't tell me. No, I'm just kidding. But again, basically, if you understand that K, right, if we have a large value of K, that means we should mainly have products at equilibrium. And in order to really make products at equilibrium, you probably need a spontaneous reaction to occur, right, to head from reactants to products, which means you should end up with a negative delta G. So again, those two things should agree with each other. Just like normal, if we have a smaller value of K, that means when we reach equilibrium, we should mainly have reactants. And what that would mean is probably your reaction is not going to be very spontaneous. It's going to be non-spontaneous, kind of hang out at the reactant side. And again, those two things should really agree with each other. And if you have an equilibrium constant that's equal to 1, your delta G will probably equal 0. And reactants and products are comparatively sort of abundant at that point. All right, so why don't you give this a go, see what you come up with. I do another delta G value from a table. The O2 value is 0 kilojoules. All right, calculate the equilibrium constant Kp for this reaction. Given that information, and again at the bottom here are some table type. Okay, let's take a look here. So in this case, we want to calculate the equilibrium constant. Doesn't matter, it's Kp. It doesn't. And remember that it doesn't really matter the letter. We've seen a lot of K values up to this point, but they're all really just equilibrium constants. So it doesn't really matter if it's A, B, C, D, F, G. So that narrows down the equation we probably should use here to the one that obviously involves the equilibrium constant. So in this case, we do have R, which is a constant, 8.314 joules per Kelvin per mole. We do have our temperature here that we need to add 273 to give us 298. Delta G we are not given, and we are looking for K. So we will find delta G by going to the table, and we would look up these values, and we would do our products minus our reactants. So our delta G here, delta G of our products minus our reactants in this case. So starting on our product side, we have 3 times 0 for the value there of O2, minus on the reactant side 2 times 163.4. Going to give us a delta G in this case of 2 times 163.4 minus 326.8 kilojoules. So now we have our delta G, we have our R, we have our T. Again, that's going to allow us to solve for natural log of K, or K in this case. We do have, again, some unit issues we want to make sure we don't overlook. That's kilojoules, that is joules. So once again, you got to do some type of conversion here. So I'm going to take my delta G here of 326.8. I'm going to times it by 1,000 to convert that into joules. That would be equal to negative our 8.314, our 298, and our natural log of K. We're going to bring all this stuff basically to the other side, and we're not going to forget to also take the negative with it, because that's going to be a little bit important here. 326.8 times 1,000 divided by 8.314 divided by 298, and the negative and the negative pretty much cancel each other out, giving you 131.9 equals the natural log of K. Any questions so far? Get rid of the natural log. We're going to do the E of both sides there. So we're going to E that guy up. We're going to E that guy, and we're not going to add a negative or anything like that. When you do the natural log and the E, that basically just becomes K. And if you do this here, and I'll just take the whole number that's in my calculators. So depending on where you round, make a slightly different number, but about 1.9 times 10 to the 57 in this case. Any questions on that calculation there? Yeah. Doesn't matter if you convert it to kilojoules, it doesn't, but they just need to be the same. You should technically end up with the same number. Again, you might get a slightly different number. The back part of the number should be okay, the 57 part, but the front part might be a slightly different depending on if you round it a little bit, especially when you do sort of the E and that part of the calculation. But if you converted this guy into kilojoules and left this guy in kilojoules, it should come out the same. Yep. Other questions? And we can see a couple of things here to make sure that our numbers do sort of agree. I got me a negative value here for delta G, which means this reaction should be kind of spontaneous heading to the product side. And I got me a pretty good large value there, K, which would back that up, right? That we should have a lot of products, obviously, when we reach equilibrium here. Any questions about that? Yeah. Yeah, there's really truthfully not very much numbers in here. So you really could have took it anywhere. I just went to 2 based off of that number, which was kind of the only number there. Other questions? All right, then let's try this one here. Calculate the delta G naught for the following. If the KSP is 1.7 times 10 to the minus 6. And there's our equation. Okay, so once again here, we do have a equilibrium constant value given to us, doesn't matter what type. So that makes our decision probably pretty simple to roll with the same equation. In this case, we actually got everything on this side given to us. Obviously, we've done that before, 298. So putting those in here, our delta G naught will equal minus our T that's been converted to Kelvin, and our natural log here of the actual K value that was given to us, which is that. So natural log there of 1.7 to the -6 times 8.314 and times the 298. And we still got the negative there. That's going to give us a 32914. These would actually be in joules, are about 32.9 kilojoules in this particular case. First off, any question on that calculation? Reaction spontaneous, non-spontaneous? We have a positive value here, which means pretty much non-spontaneous. We should expect a lot of reactants, which does match right with our KSP value. As we talked about KSP, right? Those are pretty much things that are insoluble, right? They stay on sort of the reactant side. So we have a small value of K that matches our positive value of G. So again, those things should agree with each other when you think about them. Any questions on those? Yeah. All right, one last one here. The delta G naught for the following reaction is 2.6 kilojoules. In one experiment, you got a pressure of H2 of 4.26, I2 0.024, and HI of 0.23. What is the delta G of this reaction? And which way should this reaction be headed? Okay, let's take a look. So in this case, we're actually looking for the delta G. They give us the delta G naught, so those are obviously two delta Gs. So that seems like this would be the good equation to perhaps use. Remember that this is plus here. The other thing is we also are given some pressures, and these pressures are not 1 atmosphere, which means that's really the non-standard part of this sort of reaction here. So that is, again, a case why we would want to use this equation. They were nice enough to give us the delta G naught, which would be the table value that you would get from taking products minus reactants. So we don't actually have to calculate that. We do have our R value here. We do have our temperature of 298. Once again, we do have some issues with some units we got to watch out for as well. And we do need to calculate Q, which we can from the pressures here. So Q in this case would be the partial pressure of HI, and we do need to square it like normal for the 2 that is there, divided by the partial pressure of H2 and the partial pressure of I2. And again, these pressures are really not the standard pressures of 1 atmosphere, so that is why we're using this equation. So we'll do our 0.23 and square it. We'll divide it by our H2, which was 4.26, and our I2, 0.024. That's going to give us a Q value here of 0.5174, I believe. Now we pretty much have everything that we need to solve for what we're looking for here. So we'll put our values in. I'm going to go with a delta G equals, once again, I'm going to multiply by 1,000 to put mine into joules. If you would rather turn your R into kilojoules, you could do that as well. Plus our 8.314, our 298, and our natural log of basically 0.5174 in this case. All right, so taking that there, gonna natural log our Q, gonna times it by 298, gonna times it by 8.314. I'm then going to add that to 2.6 multiplied by 1,000 to convert it into joules. And I believe I end up with a delta G here of about 967. These actually would be joules in my case. Or if you wanted kilojoules, you would have something in this neck of the woods there. Should do that. Question on that one there. Now, is this reaction favor reactants, products? Which way should it be heading? Yeah, it should actually be heading really that way, right? Kind of staying on the reactant side as we have a positive value for delta G. We still had a positive value for delta G under standard conditions. So even playing with the pressures in this particular case didn't really turn this reaction into kind of like a spontaneous reaction or to head to the product side. Any questions on any of the calculation there? We're off to chapter 17, which is electrochemistry. So we're going to talk really about redox reactions in this chapter. We're really going to mainly focus in on galvanic cells, which is a type of redox reaction. We'll talk a little bit about batteries and then some, what do they call that, electrolysis at the end. At the beginning here, I'm going to go over all the basics of redox because depending maybe on who you had for Chem 50 or whatever, maybe you did a lot of it, maybe you didn't do a lot of it. That way, hopefully everybody will be on the same page. So we're going to go through sort of redox reactions, how to balance them properly, oxidation states, again, just to make sure hopefully everybody is on the same page. So let's start with redox reactions. Redox reactions basically are as you might remember, maybe from Chem 50, is really a big classification of a reaction. It is really one of the reasons why reactions take place. There's really three reasons why reactions take place, and three of them are a solid is formed and water is made. And those are two things that occur in double displacement reactions, like precipitation reactions and acid-base reactions. The third reason why really reaction takes place is an electron being transferred, which is basically the redox aspect of it. And redox reactions cover reactions like synthesis reactions, combination reactions, decomposition reactions, single replacement reactions, and combustion reactions basically fall under that sort of umbrella of redox reactions is basically what they are. So what happens in terms of redox reactions, it really stands for oxidation and reduction. And by the way, they always occur together. So if somebody gets oxidized, somebody else gets reduced and vice versa. So it never just part of it happens. It always happens together. And there's really three definitions for each of these. And in general chemistry, we oftentimes look at the electrons. So oxidation means loss of electrons. Reduction means that you gain electrons. And sometimes people like to remember Leo the lion goes grr, loss of electrons, oxidation, gaining of electrons, reduction. Other people are popularized the oil rig version of that. Oxidizing is losing, reducing is gaining. You could put Leo the lion on the oil rig and he goes grr. You don't have to choose. You can use them all together, right? But that's basically kind of the definitions that we oftentimes will look at in general chemistry. And sometimes people want to figure out, what is being oxidized, what is being reduced. And sometimes people struggle with that. And it's really important in this chapter for you to be able to look at a reaction and sort of understand what is being oxidized and what is being reduced. So there really is a very simple way that you can figure out if something is being oxidized or reduced. You could just use a basic number line. And basically to the right there of zero is typically positive numbers. To the left is negative numbers. And as we'll talk about here in this chapter, what we look at to help us determine whether or not something is being oxidized or reduced is what is sometimes referred to as the oxidation number or the oxidation state, which, as we will talk about, is really different sometimes than the normal charges we associate with elements. They're sort of their charge and their situation. And what happens when somebody loses electrons is they now have less electrons than protons, which means they become more positive. And if you look at the oxidation state of somebody on the reactive side to the product side, and you see it moving in sort of this direction, in the positive direction, that substance is going through oxidation. When somebody gains electrons, they now are more negative than they started with, and that's because they basically gained those electrons. That would mean they're moving in the more negative direction, and that guy would be going through what is referred to as reduction. So that's a really simple way you can kind of figure out, is somebody being oxidized? Is somebody being reduced? For example, if you had iron 2 chloride going to like iron 3 chloride, the oxidation state of this guy is +2. The iron here is +3. So if you went to your chart here, +2 is here, ended at +3, moving in that direction. So we could see that the iron is being oxidized in this particular case. If you had something like oxygen on one side, and then oxygen in a formula that say has a -2 charge on this side, oxidation state of this guy would be 0, this guy would be -2. So oxygen in this case started at 0, ended at -2, moving to the left there. So it's going through reduction and gaining electrons. So that's a really sort of simple way to figure out what is being oxidized and what is being reduced. There are a couple of other definitions that we come across occasionally, but we don't use very much in here. If something is being oxidized, it also means that it is gaining oxygen as you go from reactants to products. And it could also mean that you are losing hydrogen as you go from reactants to products. So those are two other sort of definitions of oxidation, and two other definition reductions, basically the opposite of those. You will lose oxygen as you go from reactants to products if you're being reduced, and you will gain hydrogen as you go from reactants to products if you're being reduced. I would say in a lot of cases, the sort of oxygen hydrogen definition is used a lot in organic chemistry, because in organic chemistry, we deal with a lot of nonmetals and nonmetals, so there's not a lot of maybe metals involved. So a lot of times we kind of look at either oxygen or hydrogen being lost or gained. It's a very common way. But in general chemistry, we oftentimes will focus more on the sort of electron definition. Question on that there. So as we look at some of this here, electrochemical processes like redox reactions are involved when energy is released by a spontaneous reaction. And really those electrons are used to really do some type of work. So it's very similar, as we'll talk about later on in this chapter, when we talk about a battery. We put a battery into our whatever, and there's like a little wire in there. It's basically a redox reaction. Electrons go through the wire, power your device, go back to the other side. So that is sort of the same idea. What happens a lot of times in, say, galvanic cells is pretty much what's going on here. In this particular reaction here, we have really a synthesis reaction, which is a redox reaction. We have magnesium plus oxygen makes some magnesium oxide. It's also a combustion reaction because there's oxygen. If we were to assign our oxidation states for each of these things, as we might have talked about in an earlier chapter, and we'll see again officially in this chapter, anything that is in its natural state uncombined will have an oxidation number or state of 0. So this guy is 0. This guy is also 0. That is naturally how oxygen comes. Remember that things only really gain charges in a sense when metals and nonmetals come together, right? That's sort of when we make an ionic compound, those guys gain charges. And because this is an ionic compound, it would have the normal sort of oxidation states that we would imagine. Magnesium is group 2 +2, oxygen is -2. So once again, we could apply our number line if you're not sure what's going on. Magnesium is starting at 0. It's ending at +2 on the other side. So it is definitely becoming more positive. So this guy is going through oxidation. The nice thing about oxidation and reduction reactions is if you are able to figure out one thing, what is being oxidized, what is being reduced, pretty much the other thing is happening to the other guy. So by default, this guy would then be going through reduction. We could also see that by going to the number line, starting at 0, ending at -2. So our oxygen is definitely going in the negative direction here. So it's going through reduction. By the way, the things that are being oxidized and reduced are found on the left-hand side of the arrow. They're reactants in this particular case. We could actually write two half reactions to describe what is going on here. One is what is sometimes referred to as the oxidation half reaction. The other one is the reduction half reaction. And in the case of the oxidation half reaction, the electrons should always be found on the product side, like they're being given off or lost, or they're being released. And on the reduction half reaction, we have our oxygen in this particular example gaining the electrons. So electrons should always be on the reactant side in a reduction half reaction, like they are being gained. They're called half reactions because, frankly, if you were to add both of these reactions together, you could cancel out anything on opposite sides of the arrow. The one thing that should always cancel out before you add half reactions together are electrons. You always have to have the same number of electrons in each half reaction. And that is because one gives it away and the other one accepts it. So the same number of electrons are being transferred. So the electrons in this case would cancel, and everybody on the left-hand side of the arrow would stay there. Everybody on the right-hand side of the arrow would stay there. These are two ions that would come together to make our ionic compound here. So that, again, is why it's referred to as a half reaction. Another important aspect of this is sometimes we're asked, what is the oxidizing agent or the reducing agent? And that is a different question than what is being oxidized and what is being reduced. So the oxidizing agent is always the substance that gets reduced. And the reducing agent is always the substance that gets oxidized. And the reason they're called those things is, for example, here, the magnesium here is going through oxidation, which means it is the reducing agent. The oxygen is going through reduction, which means it is the oxidizing agent in this case. And the reason for that is it causes that effect in the other thing. So when magnesium loses its electrons, that allows somebody else to gain electrons and be reduced. So it's causing the reduction of the other thing. And when oxygen obviously gains those electrons, the only way it could gain electrons is to cause somebody to lose electrons. And that means it's going through oxidation. So it's always the opposite when you're asked about the agent versus, say, what is being oxidized, what is being reduced. Any questions about there? All right, we'll lay it up there, I think, for today.